So my topic will be solutions to the Einstein equations with low regularity. And this is something I've been working on for years, and especially the topic I want to talk about today. This is something that took us a couple of years to really converge to set up that we like. So mostly what I will be talking about today is a joint work with Bruno LeFloch and Gabriele Veneziano. And what we have been doing here is to construct solutions, Einstein spacetimes, so Lorentzian manifolds, that have singularities. And again, this is something I've been interested for a couple of years to define low regularity solutions, metrics, or even in a weak sense of distributions. So this will be in that spirit, but I really would like to focus on one specific issue, which is a construction of cosmological spacetimes when you succeed to go through the singularity of the spacetime. So this is a little bit unusual if you have not looked at this problem, but I think it's a very interesting problem that should be of interest for some of you. So what we have done is to revisit the notion of junction conditions across hypersurfaces. You certainly know the work of Israel many years ago, and he had junction conditions to cross regularity hypersurfaces. So situation where on both sides of the hypersurface, the metric is regular, the second fundamental form is irregular, and you write certain junction conditions involving these quantities. My case will be different, and we cannot use the junction conditions of Israel because we are looking at a contracting situation, and we would like to cross a singularity and expand after that. If I have time, there will be a second topic, maybe just a few slides to tell you about solutions with a low decay, but this is somehow a different topic, but we revisit the issue of asymptotic flatness in this case. So let's start with this. So again, this is joint work with Bruno LeFloch and Gabriele Veneziano, and we started with reading some of the literature by Penrose, by Todd, Turok, and many other people. What they do is they look at the Einstein equation, they solve it coupled in the vacuum or coupled to typically a scalar field or maybe a nonlinear scalar field in some cases. And the problem here is to look at singularity hypersurfaces. For instance, in my case, it will represent collision of gravitational waves. But this is something I'm going to talk about a little bit later. But the main issue is that you have a cosmological spacetime, you have a contracting phase, and you would like to cross it and bounce and go on the other side somehow in order to and produce an expanding phase of the spacetime. So what we have done, there have been a lot of work and papers mostly by physicists in this subject, and what we wanted to do here, looking at the whole zoo of junction conditions that can be found in the literature, what we wanted to do is to find a framework that could cover the junction conditions that had been proposed so far, and more than that, understand what are all the reasonable, geometrically, physically reasonable junction conditions that can be used to glue together contracting phase and expanding phase. So the way I'm thinking of it is like a fluid interface, because I've been working in fluid dynamics also. So I think of that as a fluid interface. There is a phase where maybe you have a certain fluid, and then you jump on some other side, and you have a different phase of the same fluid. So we have been able to produce in a systematic way bouncing junction condition in the case where there is no BKL oscillation. So I have no time to really go through the BKL analysis, but roughly speaking, there are two classes of singularities, some that are called quiescent and some that have no oscillations, and on the other hand, the oscillating singularities. So here I'm talking about what is called quiescent cosmology, and there are many, there are many such solutions that are known explicitly. So the main result is the following. There are actually two results. The first point is that we introduce a notion of singularity scattering map, again, which is analog to what were called kinetic relations in a setup of fluid dynamics. And based on this notion, general notion of scattering map, meaning a map that allows you to cross a singularity, we were able to somehow make a classification and extract universal laws for this bouncing. So what we are saying is that the bouncing cannot be done arbitrarily. There are in fact a lot of constraints. And if you put all these constraints together in a way that we call three universal bouncing laws, you actually characterize all possible junctions. So you don't need to say which model you are using and you like. You have a mathematical framework in order to handle, to study all reasonable, physically and geometrically reasonable bouncing laws. Using that, so there is a second part in our theory, which is to define a cyclic spacetime, and meaning that we do glue together a contracting phase and expanding phase. We use our junction conditions to glue them together. So we have such a notion, and we use this notion in order to construct examples. And in particular, so there is an example that is more like a local construction that I will show you. And beyond that, we can also look at a global geometry in the case of plane symmetry. So the full problem, of course, is not accessible. But if you allow me to assume plane symmetry, what we have done is to study the collision of two gravitational waves and solve it in a global way. So that's basically what I would like to show you today. So let me formulate the problem by starting with the ADM formulation and introducing near a singularity hypersurface. So this will be, to begin with, it will be a general definition, and then I will specialize to something more particular in order to get existence of solutions. At this moment, I'm giving you 2 or 3 definitions. So we have a Gaussian foliation by space-like hypersurfaces, which I've denoted by like in the screen. So we have a matrix, a 4-dimensional metric is written like minus d tau square plus g of tau, and we express the ADM formulation of the Einstein equation for the induced metric and the second fundamental form. You see that in these equations, you have the contribution of the matter, and the matter is what I've called Mij. It is defined from the energy momentum tensor given from the matter. It's also defined from the energy densities that you also compute the whole energy momentum tensor, rho and J for the momentum. And as you know, you have to supplement these equations with the Einstein constraint equations. In my situations, the matter will be modeled by a scalar field. So these equations are also coupled to a wave equation in the unknown metric. So that's what we want to do. So we want to look at this ADM formulation and use such a Gaussian foliation near a singularity hypersurface. So this is something that has been done by Alan Rendell and many people. You normalize your setup so the singularity hypersurface is located at tau equals 0, and you solve either toward the past for tau negative or toward the future by prescribing certain data on the singularity. To proceed, you have to understand what data you can use on the singularity, and this will be my first issue, to understand what are the constraints on the singularity hypersurface. And they basically are going to be the usual Einstein constraint equations, which will be, degenerate, will be, in some sense, be taken in a degenerate form on the singularity hypersurface. So we derive an asymptotic system. So this is what I should remind you or explain, is that when you are close to the singularity, the observers are basically isolated from each other. They do not communicate from each other. And this is what motivates the ansatz of removing the spatial dependency in the Einstein equations in order to produce an ansatz that is essentially an ODE system. So you have this in mind, that you think of the Einstein equations as reducing to an ODE at each point on the singularity. Of course, there are some coupling. I mean, this is more complicated than that. But in the first approximation, this is something you can do. And then there is a technique called the Fuchsian method that allows you to prescribe data and solve in a neighborhood of these singularity hypersurfaces. So this is a construction that we want to do, but we want to do that by understanding what are the degrees of freedom that we have. So to do that, we begin by defining what we mean by our singularity initial data set. And what it is, and you will see in a second. Maybe I should show you the first two parts to give you more understanding. So if you look at the second part of this screen tells you that a past asymptotic profile associated to some data will be a flow, will be an ancient geometric flow, meaning a flow defined for all negative times, which is given explicitly, like I'm writing here. There's a metric G star, a second fundamental form, if you like, K star, and a matter phi star, given by certain formula. If you look at this formula, you see that they blow up when tau is going to 0, like tau to some power, or 1 over tau, or log of tau. So they blow up, and these expressions are given in terms of data, and the data are what I've denoted G minus K minus phi 0 minus phi 1 minus. So this will be my data on the singularity, which I need to to study, because this is what is going to tell me how I can do the junction from one side to the other side. So in the first part of this screen, I wrote the conditions that you can deduce from the Einstein constraints that are satisfied on every slice. And if you approach the singularity, on the singularity, exactly on the singularity, modulo some rescaling, this is a system that you see. So you have a Riemannian metric on the singularity. You have a condition, you have a tensor that is CMC, so trace of this K minus is just 1. And then you have the Hamiltonian constraint that has become purely algebraic, and you have a momentum constraint that is basically of the form it was in the first place. So I'm now calling the space of all singularity data the solutions of this system. So these are the freedom that I have on a singularity in order to generate an ancient geometric flow. So this is a picture to try to illustrate the situation. And so what we can do, we can look at examples, and the first example would be, of course, Kastner, but I'm writing here it in a slightly general setup where I allow some X dependency in the coefficients. So K will be a diagonal in some suitable coordinates, and I wrote below what you know for the Kastner metric, and for G star, K star, and the corresponding matter content. And under certain conditions, I don't need to write here, this is really an asymptotic profile in the sense I just defined. Okay, and you observe that you have some tau dependency, which is the one that you know from Kastner. In addition, there is some X dependency that is allowed, X being some point on your on the singularity hypersurface. So what we do is that. So at this stage, this only tell us. So if I just go back here, we just have a notion of data on the singularity and a way to define something you could think of as an approximate solution to the Einstein equations. Okay, so you don't have any space-time yet. So it will come next. So we have this idea that the singularity hypersurface is regarded as an interface between two phases of some material, some fluid, if you like. So I have good reasons. I mean, a connection that I know behind this. And what we would like to do, we would like to glue together two asymptotic profiles. And in order to do that, and get an ansatz in a vicinity of the singularity hypersurface, we need a certain map, which we call Singularity Scattering Map, past to future Singularity Scattering Map. And it's simply a map that takes the data on one side with a plus, to data on the other side in the future with a plus sign. This will be for a space-like hypersurface, but we also do the construction even for time-like hypersurfaces. There is a condition, I mean, there's a couple of conditions that we would like to put, which we believe are very natural. And the first condition that we have in mind is that this locality property is that if you define a junction condition, this junction condition should be local in the sense that I wrote here. So the image should only depend on the restriction of the data on any open set in your hypersurface. In fact, and this condition can be expressed by saying that the map involves the data before and derivatives. So it's really defined in some kind of pointwise form. And then we have 2 or 3 additional conditions which have various motivations, but in particular this idea of the map to be ultra local, maybe pointwise would be another terminology. So where we would like the map to only depend on the local value at a point on the singularity. So that's essentially this condition that we use in order to generate our classification. So as you will see in a few minutes, we have a full classification of the maps where we have the constraints, asymptotic constraints imposed, and we require that the junction is based on this pointwise condition. So let me show you that. Maybe before I want to mention that what I call quiescent, and were defined actually by Barrow. Barrow defined the notion of quiescent singularities. They correspond to this condition that the second fundamental form should be positive on the singularity. So we are not looking at BKL oscillations. We are looking at a family of spacetimes that have a definite behavior, singular behavior, but a definite behavior on the singularity. Then we continue. So again, there will be definitions. So I don't know if I should stop sometimes and ask if there are any questions.
I think you can just assume that if somebody wants to ask a question, Joe will write. So
okay, let me know. So okay, so we have maybe 1 or 2 more definitions before I can really state a theorem. So just be patient. So the next definition is that we fix now a singularity scattering map. So I'll tell you how the jump should be done. And then we will call a spacetime S cyclic if it is a smooth manifold, a smooth Lorentz metric, and a certain scalar field on top of that. Smoothness is assumed outside some singular locus, and then we impose various conditions on this Lorentzian manifold. So we impose that the evolution and constraint Einstein equations are satisfied together with a wave equation for the scalar field, but we do that only outside the singularity hypersurfaces. And then near a point of the singular locus, we assume that there is a Gaussian foliation, like I described before, exactly the same setup. And then we impose our junction condition, that is, we say that the plus metric k and phi 0, phi 1 on the plus side in the future is a certain map apply the map to the data in the past. And the values plus or minus are obtained from the solution by somehow undoing what was somehow done in the description of this asymptotic profile. So G, K, phi in this limit are just my solution of the Einstein equations, my general metric and scalar field, and I'm taking the limit. I'm assuming that this limit exists, so it does blow up with a certain rate as specified here, and I assume that this limit exists. So it's a class of spacetime that are smooth everywhere except some certain locus of singularity, where this condition, these limits on both sides exist, and the connection between the two is given by a certain map that I have fixed from the beginning. Okay, so it's again another definition you can take, and now the question comes whether these sort of things exist, and so that's what the first result that we have done, gluing technique. So we have a local theory where we take any three manifold, we assume that we have a certain map that preserves the sign of capital K, like I explained before, and we pick up some data on the singularity on one side, and of course, using the maps that I'm going to apply, we have also the data on the other side, and basically we use this Fuchsian argument to continue the solution from the data on the singularity to the future, and also to the past. Okay, and so we do get a cyclic spacetime where the singularity locus exactly the manifold that we have picked up, and the junction condition that I impose is satisfied, and we have some properties that should be expected, like the volume going to zero, the mean curvature blowing up, and the scalar curvature has also some specified blow-up behavior. Okay, so I gave you, a notion of singular Lorentzian manifolds, and here a local construction. Okay, so at this moment we cannot do more without any symmetry assumption. So the next existence result will be with assuming certain symmetry, plane symmetry assumptions. So I'm going to move to that, but I think this opens the way to say you can construct a lot of new solutions, of new space-time that I think are interesting. Now, the main contribution is not quite that. So our main contribution is what I want to show you now. So the main contribution is to observe that these bouncing conditions can be classified. So we have a classification of all possible junctions, and this is really the main contribution. And the way we do it is that we work with general spacetimes, and this is why I show you the previous result. So this point of view to say, let's look at general spacetimes is more fruitful than looking at symmetric spacetime. We will do that next, but not starting with symmetric, putting symmetries. And usually this is what people do. They impose symmetry and etc. to derive the bouncing condition. So this is not our point of view. We look at a general solution without symmetries, and we realize that in this general class of solutions, the asymptotic Einstein constraints actually have a lot of implications on what kind of junction you can do. So this is a classification which I will state in two different ways. So there is one way where I just show you some formula. So classification of singularity scattering maps. So there are in fact two restrictions that we do here. So we say it's ultra local. So think of it as pointwise. And there is another condition that it has to be rigidly conformal. But we have done a lot of different results, and the only important assumption here is that we do something pointwise, which we believe is physically completely reasonable. But this is our main assumption here. And what we say is that there are actually only two classes of such maps. So one is given by, we call it isotropic conformal bonds, and it's given by just the conformal factor that depends on the matter content, phi 0, phi 1, and it only depends on the determinant of K minus. The constant phi is not very important. And after the bounce, K plus is just, the delta over 3. It's just the round metric. And the second class is what we call the non-isotropic conformal bounce. And it's a little bit more complicated, but it's just given by a single function f of phi, f here that depends on the matter field. Okay, and you look at the formula, so G plus the metric after the bounce is a conformal version of the metric G minus, and K plus, if you look at the trace-free part, the trace-free part is rescaled by essentially the same factor, mu square or mu to minus 3, and mu is given by some explicit formula depending on some f, and that's it. So you don't need to say, you don't need to postulate anything. Maybe then you want to, at some point, to make a choice of some f and understand the connection with some high order physics. And that's something we are very much interested in. But at this level, if you want to study mathematically this kind of spacetimes, you can just say, I have to prescribe a certain function phi of f of phi, and then or lambda, and then everything is under control, and you can ask questions like, doing global constructions. That's what we do in a plane symmetric case next, and you can ask then questions about global behavior of these spacetimes. So it really tells you that you have a very well defined class of singular Lorentzian manifolds you can focus on, and only that essentially. Okay, and now the same result we notice that can be formulated as 3 different laws. So we are quite happy to realize that. So there is so what I'm doing now is I'm rewriting with a little bit less details, but essentially I'm rewriting the previous page, but in a way that I state it as 3 different laws. So there is a law that tells you how the Kastner exponents should be scaled when you cross the singularity. And to do that, you just need a constant gamma, which we call dissipation constant. But I'm not sure the terminology is very good, but there is just a constant. Then we have a second law, which we call the canonical transformation of matter. And it says that the second ingredient you need to do the bouncing is a map, is a single map that acts on the matter data. So essentially phi 0, phi 1, or the momentum conjugate. So it's not so important to see what these variables are exactly, but the point is that the matter satisfies a wave equation. So you know that a wave equation has 2 degrees of freedom. So this is what this map is telling you. These 2 degrees of freedom of the wave equation can have to be transformed when you cross the singularity, but they are transformed in a way that is given by a map phi that preserve a certain volume form. And in fact, it's more specialized than that, because it only depends on a certain scalar invariance that you compute from the geometry. So K0 is a trace-free part of K. And then after you have understood that, there is a formula to express the metric after the bounce from the metric before the bounce. So we call it directional metric scaling. And depending whether we are in the isotropic or non-isotropic case, we have in one case is sigma 0, sigma 1, sigma 2. They are just any constant. So it's really a very, geometrically, it's a very beautiful formula. And if you want something that is non-isotropic, then you have to allow yourself a contribution from the matter and from this canonical map, capital phi. Okay, so essentially that's the first part of what I wanted to present. Is here we have 3 laws for the bouncing. They are universal. of course, they depend on the assumptions that we assume a scalar field, right? So you may ask, what happens if I do something else, other matter fields? And the point is that the details of this phi, of the structure about the map phi, of course, will be slightly different. But the philosophy is completely the same. You need a bouncing for the matter field, bouncing law, and this bouncing law is very restricted geometrically, and in the end of the day, it's just described by, in this case, a scalar invariant, computed from the geometry. So everything is very limited in that sense. So this is what we have done here, and at this moment we are applying it to various models. So if you look at the physics papers, a lot of papers. So my co-authors are theoretical physicists, and they know more about that, and they are moving into this subject very actively. And on the other hand, we have here new classes of singular Lorentzian manifolds, in which I think, they deserve to be studied in a more systematic way. I put two references in. You can look at that. Especially there is one. Maybe the second one is a short paper of maybe just 6 pages. So it's really easy to grasp the subject by starting with this, or maybe the introduction. The first paper is quite long, but the introduction, we try to put as much information in the introduction as we could. Are there any questions?
Let's see. In the chat, there are no questions at the moment.
Okay, thanks. So let me move forward. So what I would like to do now is to apply these ideas to solve a problem that somehow goes back to Penrose and things that Penrose had looked at. So I would like to look at the global collision of two gravitational plane waves. So obviously, from the previous analysis, we would like to go beyond cosmological singularities using our scattering maps. And the way it goes is that we are going to describe arbitrarily radiation data at past infinity. So I will show you a picture in a few minutes. And we want, so giving some radiation from infinity, we would like to determine the whole future and the global development, the global Cauchy development of such data coming from two plane waves. So as we will see, there will be expanding and contracting phases in this universe, and successive periods of such phases. There could be finitely many or infinitely many such cycles, depending on basically the duration of these gravitational waves, where what comes in can generate finitely many or infinitely many cycles. And so the theorem is a little bit, complicated to state. So I state it in a maybe schematic way, but what we prove is a global existence of cyclic spacetimes based on a prescribed singularity scattering map. So again, two plane symmetric gravitational waves collide along a two plane. What we do is that we solve the characteristic initial value problem and produce the global Cauchy development in the sense that we have defined. So it's S cyclic spacetime. And this manifold is made of a concatenation of a family of anisotropic cosmological spacetime domains, which at some point we call diamonds, or at least pieces of that. We use this terminology at some point in the construction. And these regions are separated by singularity hypersurfaces, time-like, null, or space-like. And we have finitely many of them on any compact set, but possibly infinitely many depending on the incoming radiation data. The Einstein equations are satisfied away from the singularity hypersurfaces. The junction scattering conditions are satisfied on the singularities, and the curvature blows up on the singularity hypersurfaces, exactly like I described when analyzing a single hypersurface. So I have, I mean, I can give you a lot of details, but I think a lot would be too much. So I will sketch some ideas that come in this construction. And to begin with, I have this figure where you see the incoming pulse. If you think of the duration, finite duration of some pulse, some gravitational pulse that is coming from infinity. So there are two incoming pulses. In the middle, you have a flat region. You can think also beyond that, there is also some flat region. And these two pulses are interacting, and they produce a region of the space-time where the curvature will blow up. There will be a singularity, and I'm going to cross the singularity and continue as far as I can the construction of this space-time. So I have now this picture. So the picture I just show you is only a small triangle in the beginning of this bigger picture, where you see regions. Let's say in the third picture, for instance, where you see the continuous lines, they represent the area of the T2 orbits of symmetry in the construction. So remember that we have plane symmetry, or in fact T2 symmetry would be better to. That's actually what we do. So every point in the picture corresponds to a T2 orbit. And these continuous lines tells you where this area is vanishing. And there is a second picture. I mean, the picture with a color tells you about the value of the area, and we put different colors depending on the value of this area. Okay, so I give you some feeling of what we are doing here. We cross the first singularity, and then we enter a new space-time region that, like the first square-like region consists of two time-like hypersurfaces and two space-like hypersurfaces, where the metric is singular, it blows up. And we apply our junction conditions, and then we continue, and you should observe that in the first picture on the top, you have some gray regions that somehow communicate, and some other pieces of the space-time that do not communicate. So there's a whole, geometry that is quite fascinating, I think. Now, how do we do this construction? So we start with a remark by Penrose, 1972, that suggested to look at plane waves and mention, this idea that it should be relevant for idealization of physical phenomena. But he also pointed out that no space-like hypersurface exists where you could pose the initial value problem globally. So you cannot embed such a plane wave in a globally hyperbolic spacetime, and so why we can do something still, because in our setup we do allow singularities. So in our generalized setup of cyclic spacetimes, meaning that we allow singularities, we can still formulate the initial value problem with two hypersurfaces and address the question of what's global development of such data. So this is what we have done, formulate the collision problem as a characteristic initial value problem. So we have these two plane waves, as I explained already, and we seek for the global Cauchy development. So I guess this has already been explained. And to build our formulation, we have to introduce null coordinates and define them in a good adapted way. So I will not discuss the details of that. But in the end of the day, you get null coordinates on the space-time quotient by the T2 action, which we call U bar. And you have also periodic coordinates on the torus symmetry orbits. And you express the metric in a form that is written here. So the announs that describe all the geometric quantity would be the conformal factor, the area of the orbits of symmetry, which we denote capital A, certain parameters that describe the Killing fields, the T2 orbits of symmetry. So there is a certain parameter associated with this, and the scalar field. So these are the data. You plug that into the Einstein equations, you get a very singular system, and you solve it, and that's the beginning of a long story. The normalization, so there are incoming radiation data which I already mentioned. So this data should be formulated also in a more geometric way. The normalization is such that U positive and U bar positive is really the region of interaction in our setup. There's some normalization. I guess this is really something I skip. I really would like to show you something more beyond that. So we have incoming radiation data. It turns out to be this psi associated with the two Killing fields and the matter field, phi, the scalar field. So these are the only data that you need to prescribe. And I guess physically it makes, or maybe geometrically as well, it makes sense. And all the rest of the data can be recovered from psi and phi. So then you solve the equation. But of course, the problem is that this is singular, and it's quite tricky to figure out the behavior of the solutions. But okay, I'm not talking about that here. I just want to mention that behind the Einstein equation, there is a wave equation for the area, and this is the source of the fact that the area function can vanish. So we study that. It's also the way that we see an argument to prove the infinite focusing phenomena found by Penrose. And again, I have another picture here to illustrate what we are doing. So we have a setup. We fix these null coordinates in a certain way. The normalization is very important. Otherwise, you don't know where your hypersurfaces are located. So we need to do this construction carefully. And then at some point, we arrive to this, what we call diamond decomposition. We expect finitely many or infinitely many contracting, expanding phases. And this will be described by a collection of space-time domains. So each domain will be an isotropic cosmological region. And there is a certain classification here also, where we describe it in different coordinates. And basically, we have maybe the first three figures would correspond to a space-like hypersurface, and we have enclosed by a characteristic diamond that correspond to the light cone behavior, and the next three pictures would correspond to a time-like singularity. And so we do a construction in each of these diamonds, and then we collect them together by checking, that the construction is consistent. So I'm almost at the end of what I wanted to show you. So you may wonder how these singularity scattering maps reduce, or how they are expressed in the case of plane symmetry. So I essentially rewrote what I had already written before, but it's a little bit specialized to the plane symmetry case. And again, there is a single function f in this construction. So there is a theta, whatever, theta minus is a certain Kastner angles that we introduce to characterize the second fundamental form K minus. And then we realize, we claim, we prove actually that the classification leads to choosing a single function f of this Kastner angle and the matter field phi 0. Okay, so it only depends. It's only a function depending on these two quantities that allows you to do the whole construction. And again, such a function is somehow computable if you tell me that you like such or such, high order gravity model, then I can compute this function, if not explicitly, essentially maybe implicitly, but we can say what it is in a number of examples. Okay, I guess maybe, do I have a few more minutes?
Sure, yes. Yes,
Okay.
you do have
Okay.
7 or 8 minutes left.
Okay, thanks. So I would like to show you, actually, maybe that's a bit unusual, but I have a movie that represents what I show you. So let me try. Yeah. So I need to share, because I have that in a Google. So I need, I guess, to return to share.
I'm not sure. Maybe you need to
Can I do that?
sharing and open another one with a different window, but I'm not sure. Maybe some of the local organizers can.
Okay. Maybe I know. Okay, I think I'm finding it. Share content. Okay, and now I'm moving. Maybe it will just change that window. Do you see it? You are sharing two. Wait, two applications. Maybe that's too much. Two applications. Do you see something, or see it on
Yes,
the screen? But
yes.
maybe I don't know what you see on your screen, but do you see just the movie, right?
Or images, yes, a movie.
Only the movie. Okay, so let me explain. So the movie would correspond to four examples, four different spacetimes. So again, I put some radiation data, and I generate my global spacetime. And what I'm showing you here is a slice, is a t equal constant. So it's a slicing of this interaction region of my whole construction. And I've introduced a certain slicing by space-like hypersurfaces. Okay, so if you do that, and if you plot it for a certain time interval, this is what you see for different data, different possible data. So in particular, and what is plot is the area of symmetry, or maybe the radius. What we use as a radius for our pictures is exactly this area of symmetry, or square root of the area of symmetry, something like that. So whenever okay, I have something that is on my screen. Okay. Okay. Do you have any question about that? Maybe I didn't explain everything. The color corresponds to the value of the matter field. And so, for instance, when it's red, and it should be red at whenever you have this area function vanishing, so the red part is when the geometry becomes degenerate. Okay. So I guess that's probably enough for this. Let me return to see if I succeed. Sorry. Yeah, I'm not sure what okay, let me try to close. I'm closing one window, and I'm reopening what I had before. I hope I didn't lose things. So preview. Okay. Okay. Is this fine now? You see it?
Yes, perfectly. Yes.
Okay. Okay, great. So if I have a few more minutes, I'd be happy, even though it's maybe not fully in a subject of the conference, but since I mentioned it in the beginning, solution with low decay, I would like very briefly to mention that I have this result with Stekan Nguyen, where I mean, when you look at Einstein manifolds, the decay at infinity, in the case of asymptotically flat manifolds, is very important. This is a very important issue in physics and also in mathematics. So we were interested here to analyze the Einstein constraints and produce a large class of initial data set. And this is this work, because on the other hand, I have some other work where I take such an initial data set and I evolve it in time in order to produce spacetimes. Okay, so here I'm only telling you a few words about how the initial data set with general asymptotic n somehow broad behavior is done. And so again, very briefly, what you do is that you look at the Einstein constraints, Hamiltonian momentum. You view this as an elliptic system. And what you want to do is to construct general solutions. I mean, general, I'm speaking too fast. I mean that the behavior at this flatness, I would like it to be more general than Schwarzschild. And that's essentially what most people are doing. They have behavior that look like Schwarzschild. Okay, but it's quite interesting to have much more broader class of data that are not Schwarzschild type, again, in order to evolve them and construct solutions, spacetimes. So this is what we had done in this work, and it's done by something we call the seed-to solution method, where general seed data, which means you prescribe the behavior that you wish at infinity somehow, and from that I generate a solution. And maybe I will not say much more like that, just to make a little bit of connection with the other problem where I also look at the behavior on the singularity and somehow want to characterize all such data. So this paper here is philosophically also related to this sort of issue. And just to finish, the work that I done in this direction was actually motivated by this pioneering work on the so-called localization problem by Carlotto and Schoen. And what we have done is define an asymptotic localization problem, which we could solve at some critical level. That's another story, and I guess I should really stop here. Thank you very much.